Hello students, welcome back. In this particular video, we are going to see a diode characteristic where we are going to see a forward and reverse bias characteristic of a simple PN junction diode. So in studying the forward bias characteristic of a diode, what we need a variable battery, or we can say variable DC voltage source, or we can make it variable by having a potentiometer in there. So we are applying fixed voltage and the potentiometer will vary the voltage from 0 towards the maximum. Now we are going to measure the volt across a diode using a voltmeter and a current across or in series with this particular circuit, or we can say current to the diode. So that current will be measured in actually milliamperes and the voltage is in millivolts. So resistor is there. That resistor is going to protect our PN junction diode from overcurrent, or we can say the maximum current. It will be preventing the diode, and this diode will be act like a forward bias in case of this circuit. So when we are doing or performing the practical, what we are going to do, we are going to vary the voltage in step of 50 millivolt. So first reading will be at 50 millivolt. Then we are going to observe the current on current meter and we are going to write it in here. Then step of 50, 100 millivolt, then 150, then 200, then 250 up to the 400, or the maximum limit of the power supply that we are using. We are going to measure the current for it, and then we are going to draw the graph of this characteristic. So let's look in the live. So let's look in the circuit where the potentiometer is used to vary the voltage across the diode. We are using germanium diode DR25, so that it will give us a reading in terms of a milliamperes, that is called a current. We vary the voltage from 50 millivolt onwards. So you can pause the video and take the reading according to your observation table. I'm varying the voltage up to 200. So this is the reading for the 200 ampere. For 200, and we can take reading in between them as well. 250, almost 2.9. For 0.279, that is called as a maximum voltage that we are having in the circuit on y-axis, and voltage Vf on x-axis. So completing the observation table from that live video, you can draw the graph. The graph will contains the points, like for up to Vf voltage it will indicate a 0 reading. Then the graph will be changed like this, where we are getting rapidly increase in voltage. So if we drag that graph or curve towards the x-axis, we'll get a point where that point is called as a knee voltage. So this will be the knee voltage of our diode. So calculation of static or DC resistance RDC, how it is to be calculated. So just take one point, just made that point intersect to y-axis, again made that point intersect on x-axis. So now what we'll have, RDC is equal to, according to Ohm's law, V is equal to IR. So R, if you have to calculate R, that R should be equal to V divided by I. So V means Vf at that point, and I means If at that point, will give us a static or DC resistance at that point. This is the way to calculate DC resistance, or we can say static resistance. So how to calculate the dynamic resistance? Just is these are the points. So you can take any point, any 2 points. So if I take this point, if I take this point, so change in the voltage. So I am going to draw a line on y-axis for this point as well as this point. I am saying this point as A, point as B, and as well I am going to plot them on the x-axis. So what we are having, we having AB, where we are having delta IF, and we are also having delta F. So calculation of RAC is very simple. What we are going to do, delta VF upon delta IF. So The reading results in a resistance called as a AC resistance, that is also called as a dynamic resistance. So these are the three parameters we have to measure case of our forward bias characteristic of a simple PN diode. The part B of this experiment is reverse bias characteristics, where we are going to change the polarity of our VDC, or we can say a power supply. So negative terminal is connected to P type of semiconductor and this positive is connected to N type. So we are saying that the actually our diode is reverse biased. So we have to see the characteristic of the reverse bias. So for that purpose we are going to connect a voltmeter, so that is going to measure a voltage across this particular plus and the diode's P terminal, or we can say anode terminal, and then we are having a current measurement. So that current is measured in series with this particular n junction diode. So what we are going to do, we are going to vary the voltage like 1 volt, 2 volt, up to 9 or 10 volt. So this actually these are actually, you can see these are the positive voltage, but according to this PN junction diode these are actually the negative voltages. Okay, so according to each input volt, or we can say the voltage applied to the PN junction diode, we are going to measure the current, and that current is measured in microampere. So let's look how in the lab we can do this experiment. So let's look. Reverse bias resistance is connected and I am going to vary the voltage as like I have it to 1 volt. We are going to test the reading, that is 2.8. Going to put 2 volt in 2.8. Going to vary the voltage 3, 2.8, same reading. For 0 it is actually 0 reading. For 4 volt we are getting slightly change, comes 2.9 actually. Then I increase the voltage beyond 6, 2.9, same. For 7 it, for 8, 9, 10 it is. So this is the way in which we plot the graph of voltage in this direction. Because it is negative, we are getting a current that is also a negative, because we are getting the reverse current, or we can say reverse voltage applied to this PN junction diode if we treat P and N to be as a forward bias characteristic. So in reverse biases, the voltage polarity and the current polarity is negative. So we are going into a third quadrant, or quadrant third. So what we are getting for 0 volt, we are getting 0 reading, and if we are increase it to in the direction, we are getting very less change. We are not going beyond this point, that is called as a breakdown voltage. We are sticking up to the breakdown voltage because the diode has a very large breakdown voltage. So in practical we are going up to 10 volts, so that we are not going to the breakdown voltage. We are getting a graph like up to this. Okay, so now we have to calculate a reverse saturation current. So if we draw the let me erase. If I draw back this particular graph to the x-axis, okay, so that particular, we can say this is to be as a reverse saturation current. So for that particular voltage we are getting a current that is a reverse saturation current. So you can see here the voltage is actually in x-axis, current actually in this y-axis. So what we are getting, we are getting from 0 towards a 10 volt, we are getting a graph, and that having a very small change. If I draw a line back on x-axis, that a point where it intersect y-axis actually, that is called as a reverse saturation current. And from that reverse saturation current, if we have a graph, from that graph how we can calculate the reverse resistance. So for that purpose we need two values. If I take a point 1 in here and next point it in here, if I draw back to the y-axis as well as to the x-axis, then I'm going to get delta, what we can see, delta V, the change in voltage, and delta I, that is a change in current. So according to this, the reverse resistance R is calculated to be as delta V upon delta I. So you just take the observation table from that video, draw the graph and then plot the graph, then calculate reverse saturation and reverse resistance. So this is the way the diode characteristic practical can be done. Thank you.